Hello everyone, this is a lab prac for the synchronous machine. So the exercise objective is when you have completed this exercise, you will be able to demonstrate the non-load operation of a three-phase synchronous generator using the synchronous motor or generator module. So in the first part of the exercise, you will set up the equipment in the workstation, connect the equipment as shown in the figure given, and make the appropriate settings on the equipment. In the second part of the exercise, you will vary the speed and field current and observe how this affects the no-load operation of a three-phase synchronous generator. In the third part of the exercise, you will vary the field current of the synchronous generator by steps. For each step, you will record in the data table various electrical parameters related to the three-phase synchronous generator. You will also vary the speed of the synchronous generator by steps while recording various electrical parameters related to the synchronous generator. You will use the recorded data to plot various graphs and determine many of the characteristics of the three-phase synchronous generator. So first part, setting up the equipment. Install the equipment required in the EMS workstation. Mechanically couple the prime mover or dynamometer module to the synchronous motor or generator module. So here the module is already being installed. So here this is the dynamometer module, and you can see inside this is the electrical machine inside. And this one is the synchronous generator module. So inside they are already physically coupled to each other. On the power supply, make sure the main power switch is set to the off position and the voltage control knob is turned fully counterclockwise. So here this is the power supply module. Now it's in the off mode. This is the knob for adjusting the voltage. It is in the minimum value now. And here this is the knob for the exciter of the synchronous generator. It is in the minimum position now. Ensure the power supply is connected to a three-phase power source. So we have already connected the module to the three-phase power supply. Ensure the data acquisition module is connected to a USB port of the computer. So this is a USB cable and already connected to my computer. Connect the power input of the data acquisition module to the 24 volts AC output of the power supply. So this is a power supply to the data acquisition module and is already connected to the power supply. On the power supply, set the 24 volts AC power switch to the on position. So now it is off, we set it on. So if you are using the 4-quadrant dynamometer as what is used here, turn it on by setting its power input switch to the on position. So now it's off, turn it on. Press and hold the function button 3 seconds to have uncorrected torque values on the display of the 4-quadrant dynamometer. So here the uncorrected torque value means the torque value you see in the meter here is the actual value being measured. So it is not being corrected by any factors. So we use this function. So now I have already selected the mode by long press the function button in the uncorrection is uncorrect value mode. Start the metering application. In the metering window, open setup configuration file as given this, then select meter layout 2. So the software controlling this platform is already installed in the computer. So now I just need to open the software. So now here I have already select the AC motor 1.dai, this file, and select the meter layout 2. Now we need to connect the equipment as shown in figure 3. On the synchronous motor generator, set the exciter switch to the closed position and the exciter knob to 3 quarters of maximum. So here for the knob, there's a switch, and we select to the on mode, and then for the knob, adjust to the 3 quarters of maximum, roughly here. Now we need to connect the modules by referring to the circuit diagram given here. So on the diagram, you can see this is the primary mover module. This is the synchronous generator module. So internally, they are already physically connected, coupled together. Now we need to select the upper part. This is the excitation circuit, and and then the right-hand side part. This is a metering part. So for the excitation part, we need to connect DC power. Here we use this DC power to the current meter I3. And then from the meter I3, we connect it to the excitation circuit. This is the excitation circuit. Go back to the negative polarity of the power source. For the synchronous generator, we need to connect the 3 voltage meters, E1, E2, and E3. So those 3 meters are measuring the output voltage for each phase from the synchronous generator. and then set the 4-quadrant dynamometer or power supply or the prime mover dynamometer to operate as a clockwise prime mover. So here we need to select as clockwise prime mover mode. Second part, synchronous generator no load operation. Turn the power supply on. Set the prime mover speed indicated by the speed meter in the metering window so that it is equal to the nominal speed of the synchronous motor. So the nominal speed of the synchronous motor as given here is 1500 rounds per minute. So now the speed of the synchronous generator, the mover for the synchronous generator is set as a nominal speed. Because it's a bit noisy, the device here, so I turn it off for now so you can hear me. In the oscilloscope window, make the appropriate setting to observe the waveform of the voltages on channel E1, E2, and E3. That is the voltage induced across each of the stator windings of the synchronous generator. So now let's use the oscilloscope in the metering window to see the output values. Now I have select the display of the oscilloscope in the window, metering window, to show the output voltages of the synchronous generator. I will move the cameras closer so you can see clearly. Now I will turn on the primary mover again. We need to adjust the display of the oscilloscope so you can see the complete waveform. Now you have the waveform of the output voltage. So you need to answer the questions by referring to those waveforms. Are the waveforms or sinusoidal? What is the appropriate phase shift between each of the voltage waveforms? In the oscilloscope, select the display continuous refresh functions. I have already selected this. Here. Slowly adjust the prime mover speed until it is approximately equal to 1000 rounds per minute. While doing this, observe the waveform of the voltage on channels E1, E2, and E3 in the oscilloscope window. So now I will adjust the knob here. This knob is controlling the speed of the primary mover. I will reduce the speed to 1000 rounds per minute. And then you need to observe the waveform showing here. I start reducing the speed. Now the speed has reduced from 1500 to 1000. The waveform changed accordingly. How do the amplitude and frequency of the voltage waveforms vary when the speed of the synchronous generator is decreased? Briefly explain why. Does varying the speed of the synchronous generator affect the phase shift between the voltage waveforms, and why? On the synchronous motor or generator, slowly turn the exciter knob counterclockwise to decrease the field current IF. When doing so, observe the waveform of voltages on channels E1, E2, and E3 of the oscilloscope. So now I will reduce the excitation current by adjusting this knob here. I will turn this knob, and at the same time, please observe the oscilloscope. Now I start decreasing the excitation current. How does the amplitude of the voltage waveforms vary when the field current of the synchronous generator is decreased? Briefly explain why. Does varying the field current IF of the synchronous generator affect the frequency of the voltage waveforms? And the phase shift between the voltage waveforms? Why? Set the prime mover speed to 0, then turn the power supply off. I will set the speed to 0. Turn off the power supply. Now let's go to part 3, third part, characteristics of a synchronous generator. So modify the connections so that the modules are connected as shown in figure 4. Connect the 3 resistor sections on the resistive load module. This is the resistive load module here. In parallel to implement resistor R1. So, as you can refer to the lab prac document, so here this is the figure 4. As you can see in the exciter circuit, we have an extra resistor here. So now we need to connect R1 into the circuit. Now we have connect R1 using the resistive load module. Sorry. This is the resistive load module. Connect R1 into the circuit. And also for the stator winding, we need to change the connection of the 3 voltage meters. Only keep E1 here, and E1 now is measuring the line-to-line voltage. So the frequency meter in the metering window. So here in the metering window, there is a frequency meter already inside. It will be used to measure the frequency of the voltage produced by the synchronous generator. Turn the power supply on, set the prime mover speed so that it is equal to the nominal speed of the synchronous motor. So the nominal speed is still 1500. I will start later. Record the synchronous generator output voltage EO, field current IF, speed N, and frequency F in the data table. These parameters are indicated by metering E1, IF, speed, and frequency respectively. Now we need to turn the dynamometer module on and set up the speed as 1500. Now we have already set up the speed as a synchronous speed, 15 as a nominal speed, 1500. So we need to change the value of resistor R1 and vary the settings of the exciter knob. The knob is here on the synchronous motor to increase the field current to the value indicated in the following table. So in 10 steps that are spaced as equally as possible. Note that it may be necessary to short circuit resistor R1 to increase the field current to the maximum value indicated in the table. For each current setting, readjust the prime mover speed so that it remains equal to the nominal speed of the synchronous motor. Then record the data in the data table. So now we need to use, by referring to the data table, we can see in the data table, our local AC power network in Australia is around 240 volts. So for the field current, the frequency is 50 Hertz. So for the field current, our target value is 450 mA. So that is 0.45 ampere. So we need to increase from 0 to 0.45 ampere in 10 steps. Let's try to keep the steps as equally as possible. Now we need to create the data table in the computer so we can keep records of the data. Let's create data table here. We name each column of the data table. Put voltage. So here for the voltage, output voltage is measured here, field current is measured here, frequency is measured here. For the speed, this speed is not accurate because our data acquisition module, there's a cable missing. The cable should connect here to the dynamometer module so that we can measure the speed. Because the cable is missing, so we will read the speed value from here, this meter. Now I will start the 10-step adjustment and record the values accordingly. So now you can see I have already make a recording for the 10 groups of data. So what I did was I adjust the configurations. I adjusted the switch on and off for the resistors so that I can change the value of R1. And finally, I also adjusted the knob here to increase the field current into our target value. So now in the data table window, confirm that the data has been stored, entitled the data table as this name, DT611, and print the data table. Record the frequency of the voltages produced by the synchronous generator in the following blank space. This frequency is indicated in the column frequency of the data table, frequency. Calculate the theoretical frequency of the voltages produced by the lab volt synchronous motor using the following equation. So you should calculate here and derive the result. Compare the measured and calculated frequency. Are they approximately equal? In the graph window, make the appropriate setting to obtain a graph of the synchronous generator output voltage using the output voltage as a function of the field current. To plot the graph, entitle the graph as G611. Name the x-axis as a synchronous generator field current. Name the y-axis as a synchronous generator output voltage, and print the graph. So here, guys, I have already showed you the data. Later I can send a separate email to share with you the data. So use the data here. Use all the recorded data here. Use your Excel instead of using this software, this interface. You can input those data, transfer those data to your Excel software, and use the Excel to plot the graph and then attach to the report. Observe graph. Is the synchronous generator output voltage EO 0 when the field current is 0? Briefly explain why. Briefly explain why the relationship between the synchronous generator output voltage EO and the field current IF is nonlinear for high values of current IF. Now we go to the step 17. Turn the power supply on. On the synchronous motor generator module, set the exciter knob so that the field current IF, indicated by meter I field, is equal to the value given in the following table. So in the given table, we select the local AC power network as 240 volts. So the corresponding field current value is 300 mA. Now we need to record the synchronous generator output voltage EO, field current IF, speed N, and frequency in the data table. These parameters are indicated by meter E1, I field, speed, and frequency respectively, similar as the previous step. Increase the prime mover speed to the value given in the following table by increments of 200 rounds per minute. For each speed setting, record the data in the data table. So now again we need to create the data table. This is the previous data table. We need to create a new one. So we need to increase the speed from 0 to 1800, and the step is 200. So we can input the steps here because we already know the steps. Now we need to use the via the level prac to observe to get the frequency value, field current value, and output voltage value. So now the speed is 0. And we need to adjust the knob. We need to adjust the knob to configure the field current value as a 0.3. So here our field current value is 0.3 and the speed is 0. So we need to write down the output voltage value, frequency value. Just keep changing so you can write down the value you see. Now let's increase the speed to 200. Now the speed is 200. Now it's 400. $600. $800. Consultant. 1600. $1,800. Now I turn the device off, so it's stopped. We have collect all the required data. So using this data table, you can transfer the data to your Excel software and then do the plotting. So in the plotting, you make the appropriate setting to obtain a graph of the synchronous generator output voltage as a function of the speed n. So the output voltage is here, the speed n is here. Use those two to plot the graph. Entitle the graph as G612. Name the x-axis as a synchronous generator speed. Name the y-axis as a synchronous generator output voltage, and print the graph. Describe how the synchronous generator output voltage varies as the speed varies. In the plotting, also make the appropriate setting to obtain a graph of the synchronous generator frequency. Frequency is here, the last column, as a function of the speed n is here. Entitle the graph as G612-1. Name the x-axis as synchronous generator speed. Name the y-axis as synchronous generator frequency, and print the graph. Describe how the frequency of the voltages produced by the synchronous generator varies as the speed varies. We finish here now. Then I need to turn the power off. Alright everyone, so this is the synchronous machine like a prac. Now you have obtained the data. You can use your Excel spreadsheet to plot the graph. And please remember to answer the review questions at the end of the report as well. And then submit your finalized report to the GCU. Thank you.